Hi, my name is Gautam, and today I will be presenting the paper LLaRA. LLaRA stands for Large Language and Robotic Assistant, and the main purpose of the paper is to supercharge robot learning data for vision language policy. So let's go through the index. So first we will cover the overview, then we will cover method and structure, then in the end we will look at experiments and results followed by demo. Now let's look at the overview of the paper. So LLaRA is based upon large language models and vision language models. As we have seen in the recent years that large language models like GPT-4 and Llama have exhibited tremendous capabilities in reasoning, task solving, and world knowledge. And the main objective of LLaRA here is to use these models to improve robot action policy through instruction response space. And here, LLaRA leverages a novel way to make use of the auxiliary data to overcome the limitations that the current methods have with regard to spatial awareness and domain specific training. Now let's look at a little bit more about LLaRA. So LLaRA is a novel framework designed to enhance robot learning and policy generation by leveraging vision language models and formulating robot action policies as conversation. So when you give an instruction to LLaRA, it converts into robotic instruction based on large language models and vision language models, and then the instructions are passed on to the robot, which takes action real time based on vision and its current capabilities. And the development of the framework combines vision language model with large language models, as I mentioned, to generate high quality data for imitation learning. So LLaRA combines vision inputs and textual data, and this automates the generation of high quality robot instruction data using behavior cloning. Let's look at the limitations of the current approaches. So currently there are limited data diversity, which makes it insufficient to train data with different variations, and there are poor policy generalization, which means it's the robot struggles to adapt to unseen tasks or environment. Then comes shallow instructions, which means conventional model provide basic or incomplete instruction for multi-step and complex and long-term tasks. And LLaRA addresses this by enriching existing data with high quality, detailed and contextually specific vision language instruction that improve its learning using auxiliary data. Now let's look at the method and structure followed by LLaRA. So let's look at the architecture overview. So the key concept here is adaptation of vision language models to robot controlled tasks. So VLM components has a pre-trained visual encoder which processes visual inputs and a large language model which processes textual prompts and output robot actions in natural language, which then the robot follows. And the action policy is framed as instruction response space and fine tuning process. The VLM is firstly fine tuned with the custom data set from the robot behavior, and which is fine tuned upon the existing vision language model which were trained on expert trajectories. Now let's look at data generation pipelines. So one of the key concept in LLaRA is the data generation pipeline, which is what differentiates it from the existing models. So, firstly, it converts behavior cloning datasets into instruction response pairs. So, let's say an expert says to pick an object. So, so, so the rob, so the instruction would be pick up and the object at the coordinates xy and rotate by x degree or theta degrees. So these instructions are framed for robot to take actions clearly and with respect to its current situation. And step two involves automating the auxiliary dataset, such as spatial reasoning, object detection, and future prediction data. So here, the auxiliary data is generated based on these two steps, and the visual and as shown here, it's a visual representation of data flow from robot trajectory, which is passed on to the instruction tuning dataset. So here is an example of behavior cloning dataset and in, and behavior cloning dataset with instruction tuning. So let's look into instruction tuning. So the visual motor instruction tuning, where robot manipulation tasks are expressed as visual textual instructions. So we will here compare in BC, which is instruction tuning data generated from behavioral dataset, and D in BC. It stands for instruction tuning data enhanced with object detection. So we will compare the one with just instruction tuning and one with object detection in this slides. So, so for example, uh, uh, the instruction might be pick up an object at the coordinates x, y, and drop it at coordinate a, b. So this is based on object detection. So this is the architecture of LLaRA, which we are following. So first we have a visual encoder, and from which we get from where we get the images. Then it is passed on to the adapter, then to the LLM. Similarly, there is a tokenizer which takes the user input. Then it's converted into word embeddings and passed on to LLMs, and the LLM make the decision. So let's look at the auxiliary data for LLaRA for self-supervised learning. So as I mentioned, auxiliary data is the most important part of the paper. So the purpose of auxiliary data is to improve spatial temporal understanding through self-supervised auxiliary data sets. So there are six auxiliary data types: localization, detection, future prediction, spatial reasoning, temporal relationships, and action prediction. So as you see, these are the examples of each of them, each of the auxiliary data sets for visual motor instruction tuning. So let's look at the experiments and results conducted. So initially, LLaRA was tested on VIMA benchmark, which was simulated on 17 different robotic tasks, including object placement, rotation, and other manipulation tasks. And the data science include VIMA 800 to 80K. And the evaluation is done across three difficulty levels: L1, L2, and L3. And the success rate is measured across the VIMA dataset with a baseline RT2 style approaches. And we compare in BC and D in BC. And And we found that LLaRA consistently outperformed baseline models, particularly in scenarios with limited dataset. Example, VIMA 800. And compared to VIMA, the best model not only achieves better performance but also requires less input and is trained on 12% of the data used in VIMA. So the the paper shows that LLaRA adapts dynamically to the environment without requiring a lot of data to train, as it adapts to different environments quickly with the help of auxiliary data. Now this is a graph between the comparison which I explained. Now let's look at the impact of auxiliary dataset. Auxiliary dataset greatly enhance the performance in low data settings, which is VIMA 800, and different types of data types like localization detection, future prediction, and spatial relationships was the key part that helped in performing well in such scenarios. And the result we found was that by incorporating auxiliary datasets, it improves LLaRA's ability to generalize complex tasks and dynamically adapt to different environments. Now let's look at real world experiments. So in the paper, they have done different experiments in real world using robotic arm, which include grasping and other object manipulation tasks. So initially, a camera was set across the robotic arm with which is an RGB camera, and the task was to move a move objects into the bowl, rotating an object by X degrees and placing objects in a tray. And through the result, LLaRA's models, fine-tuned with real-world data, achieved a greater success than the baseline method, especially when combined with auxiliary data. So, as you see, this is a comparison. And in the end, let's look at the demo. So this is the demo of LLaRA with a real robot. So its initial goal is to pick up an carrot, rotate it to X degrees and drop it. Then step 2 is to place all other objects into the large bowl. So the LLaRA generates instructions based on this. So it found that next it has to pick a blue polka dot ring and rotate it in a certain degree and put it in the bowl. So this is an example. This is a different example of LLaRA. So here the goal is to weigh the tomato. So as you see in the screen, instructions are being generated in real time and passed on to the robot, which takes action based on the instructions. And to conclude, LLaRA's unique approach to combining behavior cloning and auxiliary data significantly improves robot action policy. And fine-tuning vision language models for specific domains, including robot learning, yields promising results. And to conclude, in both simulated and real-world settings, LLaRA achieves a greater success. And in the paper, the future focus is on exploring more auxiliary data types for even more specialized tasks, and also more expansion on more complex and multi-step robotic tasks will be done, which involves long-term planning and memory. And additionally, more diverse sensors, including depth sensors and tactile sensors, would be introduced